Okay. So today I'm starting to speak about a machine learning testing, following the chapter on machine learning testing, chapter number 5. The first thing I want to say, I want to say two things to start us off, and then I want to talk a bit about the basic concepts here. I won't cover the entire chapter today, but it will be a start. So when you have a machine learning system that includes regular software and machine learning model combined together, and they serve some business purpose. There's basically some objective function, that a business objective function that you want to achieve. We'll call it X. So X is like some random variable that you're measuring that achieves some business objective. Now, in addition to that, you have the different independent variables that you don't control, like x1, xk, that you typically want to see some relation between them and x. So you want to estimate x, meaning estimate the average, typically the average behavior of x, and the standard deviation or the variance of x. You want to estimate that given some independent variables. Okay, now to give a concrete example, you may want to, in a chatbot example, you may want to understand what's the average of number of people that is of conversation that goes to an agent. So that's something you want to estimate given different conditions on the system, the time of the day, for instance. And you want that this average, you typically want to control it. So the idea is that if this is the value of the random variable, and this is its fluctuation, you want it controlling some way between some limit, some upper limit and lower limit. Okay, so that's the basic notion, the basic idea of what you want to achieve. And in the past, in traditional systems, this is achieved as an example, achieved in a production line. So many production lines are statistically controlled. Okay, so you have that. You can estimate what's the percentage of defects, for instance, that the defected items that you're going to produce. Maybe it's 3% in the production line, and you control this. So you're okay with 3% of defected items plus minus 1%, and as long as this is what's happening, you don't stop the production line. But when this is out of control, out of this upper and lower limits, you say, oh, it's out of control, it's gone like this, so I'm not happy with it anymore, and I stop the production line. Now, the classical handling of these ideas was done in the context of statistics, but in the context of parametrics, what is called parametric statistics. Parametric statistics means, in contrast to what we're going to try to do, which we're going to be done non-parametric statistics. Okay, so what does that mean, parametric statistics? It means that we model the world according to some known distribution, and we don't know the parameters. So for instance, we say that we flip a coin, and there's a probability that the coin will be on one side, let's call it 0, and there's a probability that it's going to be on the other side. Let's say that the probability that it's going to be on side 1 is p. So p is the parameter here. It could be half, could be 1/3, it could be different numbers. So that's a parameter, and I have a model of the world. So I have two possible outcome, 1 or 0, and with probability p, I'm going to be 1. That's the world of parametric statistics. It's a well-known world. It's typically taught in regular courses, but what in undergraduate courses. But what we are interested in is the non-parametric statistics world, and the reason that we want to utilize this world is because we don't have any idea of what the parameters are. The distributions could be very complicated in the case of machine learning, so we don't know what the parameters are. That's why we need to understand non-parametric statistics. Any questions up to now? Okay, so to sum up, we are trying to control a system using some KPIs or some, key performance indicators or business indicators, quantitatively measured by a random variable. This is my X here. And I'm trying to analyze it and understand things like average, standard deviations, create control limits, and so on and so forth. But I want to use non-parametric statistics because I don't know anything really about the distribution. So this is the setting and basically of chapter 5. And let me start off by some small things I'll do today that will get us started. So the first thing to understand is what do we mean exactly by a random variable. So in order to do that, I give an example of a fair dice. The fair dice has six sides, so 6 possible outcomes. I call them 1, 2, 3, 4, 5, and 6. And I assume that I know how to talk about the probability of each subset of possible results. So because I don't know anything, right? This is one of the axioms of probability. I don't know anything about it. I don't have any preference about any of the sides of this first dice. Then I have 6 possible outcomes. Each one of them has equal chance of happening. So, as a result of that, I say that the probability of, say, getting side number 1 is 1/6, so on. And the probability of having of getting a subset of 3 items is 3/6, which is a half. So how is that connected to the concept of the random variable, which is going to be central to what we're going to do? So the random variable is a function that that takes value that goes from the set of possible outcomes that we have in our experiment to the real numbers. So, for instance, I could have here the random variable to be just the identity function. So for getting side number 1, I'm going to say I got 1. So I can ask myself, what is the probability of getting a value that is less than 3? This is here. Probability of getting a value of the random variable that is less than 3. So you see, look at the notation here. The probability of getting an element out of the possible events for which the random variable, which is the identity, is less than 3. So what are the possible items? If you take 1, then 1, the random variable is 1 and it's less than 3. 2, the random variable is 2 and is less than 3. 3, the random variable is 3 and is less than 3, because it's the identity. Now 4, the random variable will be 4 and it's not less than 3, and it's not in that set. Same thing for 5. 5, the random variable is 5 and it's not less than 3, so it's not in the set. And 6. So overall, the set here of the random variable being less than 3 is 1, 2, 3, which is 3 outcomes, so it's 3 over 6, which is half. Now the other thing we'll need in order to do this is so we'll need the concept of the random variable, and we'll need the concept of a distribution function. And the distribution function is just what's the probability of the random variable being less than a certain value. So the distribution function of 3 is the probability of the random variable being less than 3, which is 3 over 6, which is a half.
It's less than or equal to 3, right?
Yeah, less than or equal. That's why you have a line here below the less. Yes, less than or equal. Thank you. Okay. So that's the two basic concepts that we'll be playing with. One is it's actually 3 basic concepts. The most basic concept is the probability space. And then what's the probability space? It's basically you have a set and you have a distribution of the probability mass that for each element in the set give you some probability. Together it sums up to 1. And then you need the concept of a random variable, which is a way to measure some measure that you're interested in on top of this space. Okay, and then you need the concept of the distribution function, which is just the probability that the random variable would be less than a certain value. We'll see in a minute another example of a random variable, and that will help us understand this. So,
Eitan.
Yes.
Sorry, I just wanted to point out, and I know you said this a few times, but like the distribution function is the probability below or less than or equal to, not the probability of being the value. That's
right.
It's not the density function itself. It's the sum of the integration, or in this case, it's a discrete variable.
Yes. So if you look at the definition here, exactly as you said, it's the probability of the set of all elements in the space for which the random variable has a value that is less than x. So exactly as you said, this is not the density. This is the the distribution function, and it's the cumulative density for those who are familiar with density. So if you have a density, this will turn out to be the integral of the density up to the point x, from minus infinity to x. Okay. In other words, what Sam is saying is that what I'm talking about here is the distribution function at x, which is the probability of the random variable getting a value that is less than x. And if you have a density function, that would be the integral from minus infinity to x of the density function. Okay? So that was Sam's comment. So don't confuse what I call the big F with what I would call the small f. So the big F, but they, if they go backwards and forward, and as long as the random variable doesn't have just like in our case, the random variable has 6 possible values: 1, 2, 3, 4, 5, 6. We call it a discrete random variable. But if the random variable is continuous, then we use a density function. And in fact, the probability of any one point then becomes 0, because what's the probability? What's the probability of the random variable getting an exact value in the continuous case? That's basically the integral from the integral from well, basically it's I won't explain it exactly, but it's the integral from x to x of f of dx. Think about it a bit, which is actually easy. Okay, so when you the very dramatic difference, if you like, between the discrete case and the continuous case is that in the continuous case, the probability of any single point is 0. The discrete case, points have probability more than 0. In our case, 1/6. Okay. Now, so what's the distribution function of -1? So what is f of -1? What's the probability of the random variable getting a value that is less than -1 or equal to -1, as Jim was saying?
It's just the integral from minus infinity to -1 of the distribution function.
That's true, but now we're back talking about the discrete case here with the dice. So what's the probability in the case of the dice of the random variable here that I've defined, the identity, having a value that is less than -1 or equal to -1?
Well, it's not within the set, right? So it's 0.
Right. Now less than 0 and equal to 0 or equal to 0? What's the probability? What's the value of the distribution function at 0?
It's 0.
Very good. Great. Now what's the value of the distribution function at 10.1?
0.
No. 1. Okay, because it's the let's see it together. It takes a minute to understand these concepts, but then they become very easy. So what's the what's the distribution function at 0.1? So we go by the definition. It's the probability that the random variable is going to be less than or equal 0.1. Right? That's the definition. So that's basically, so at any of the points, 1, 2, 3, 4, 5, 6, the value of the random variable is going to be 1.2, 3.456, which is, all the time less than 10.1. Okay. So this is the probability of getting the set 1, 2, 3, 4, 5, 6, because the probability, the value of the random variable on 1 is 1, on 2 is 2, on 3 is 3, on 4 is 4, on 5 is 5, 6, 6, all of them is less than 10.1. So that the probability of this is 1. Okay? Is that clear?
Yeah, yes, it just seems like for a die, the probability of 10.1 is
It's a silly question.
right.
No, but it's less than it's less than 10.1.
Yeah, less than.
Right, less than or equal to, right? Yeah.
But it's still a silly question. It's a silly question that helps clarify the concept.
Right, but for some type of AI training, right? I mean, it's easy to see for the die example that it's a silly question, but if you were learning some more complex behavior, it might not be as obvious, right?
Right, but what happens? We're getting there. Well, you'll see in a minute, because we're taking the non-parametric approach. It's not the way we don't expect to be able to imagine how the distribution looks like. Okay, because it's complex and we don't understand it. Instead, there's other tricks that we use. Okay, so it's important to understand this concept of the distribution function, because that will be one of the ways to get around not understanding what the distribution is. We'll take f and we'll go for, we'll change it, we'll change f. Basically, we'll change f to something else. We'll call it fe, which is the empirical distribution. So we'll be able to estimate the distribution, the theoretical distribution based on the data without understanding the data, without modeling it. Okay? So that's why we are going down this route, basically. And so what now let's ask a realistic question. So what's the probability, what's the distribution function at 5? Let's do that one. So we're asking now, what's the distribution function at 5? So that's what? That's the probability of the random variable being less than 5. So that's the probability of 1, 2, 3, 4, 5. Less than or equal. Thank you, Jim. Jim. Yeah. So let's, 1, 2, 3, 4, 5, 6 is not in set. Okay, so that's simply 5 over 6, right? So that's 5 over 6. Okay. So basically, this is good. So we now we have a clear notion of what the distribution function is, what a random variable is. And next time we'll continue and talk about the empirical distribution that will help us analyze conduct all kind of analysis that are related to testing of machine. Okay. Any other comments or questions? Okay. So right. So thank you very much for joining today, and we'll continue next time.
Thank you, Eitan.
Thank you. Bye.